This is a video on ANOVA. This is the last video of the entire class. So I hope that you've learned a lot from these videos and that you've enjoyed them and that they will help you as you take your final exam. And in the future, if you want to go back and learn more about statistics, try and remember what we did before, you're always welcome to come back and take a look at any of these videos. What we will be talking about today is first the F distribution. We've already had the uniform distribution, the normal distribution, the student's t distribution, and the chi-squared distribution. So this is the final distribution of the quarter called the F distribution, which will be used for the one-way ANOVA test. So we'll talk about the one-way ANOVA test, which is a test to find out if many quantitative variables have the same mean, or if they don't have the same mean. And then after that, we'll actually be officially done with the class, but we have had lots and lots of hypothesis tests. I think that it's a good idea to go back and say, well, how do we know what test to use? So I want to summarize all the different tests that we've had in this class. So let's move on and talk about the F distribution. So if you remember, the t distribution and the chi-squared distribution had a different distribution for each degrees of freedom. The F distribution is similar, but there are two types of degrees of freedom for the F distribution. There's the numerator degrees of freedom and the denominator degrees of freedom. So for each pair of degrees of freedom, we get a different curve. And these are the curves that are shown for 4 different pairs of degrees of freedom. You'll notice a few things. One is that there are no negative values under these curves. So that's the good news. We don't have to worry about left tail and right tail and two-tail test. There's just one type of test. It turns out to be a right tail test because there's just a right tail for these particular curves, for the F curve. So the horizontal axis will be the F axis. We've seen the x-axis, the z-axis, the t-axis, the chi-squared axis. This will be the F axis. The vertical axis is just a number, a mathy thing. Once we've decided what the value is for that F, we could talk about the area to the right of that value, and that will be the p-value. We've understood all these things before, so hopefully you still understand this today. It's the same idea. Now let's use the F distribution by talking about one-way ANOVA. So analysis of variance is what ANOVA stands for. And it's used when we want to test the claim that 3 or more populations have the same mean. The null hypothesis, H naught, will be that all the means are the same. Mu1 equals mu2 equals mu3, all the way to the last one equals mu, whatever this last one is, mu n. The alternative hypothesis, you'd think that maybe the opposite of all the means are the same is that all the means are different, but those aren't opposites. Because you could have maybe first 5 of them the same, and then the 6th one might be different, and the 7th and 8th one might be the same. So some could be the same, some could be different, and that still violates H naught. So the way of talking about the opposite of H naught is just in words, saying at least 2 of the means differ from each other. So it turns out that ANOVA is very difficult to use. There are many, many assumptions that we have to make in order to use ANOVA, or requirements that we have to check. So let me go over the requirements. This is just an elementary statistics course, So I don't expect you to fully understand how to check the requirements, but I do want you to be aware of the requirements. The first is that all population distributions are approximately normal. That's actually a very difficult requirement to have. Now, we can have the sampling distributions are approximately normal, but then remember we have to have greater than 30 for every single sample that we're looking at. So if we're comparing 10 different means, then we're going to have hundreds and hundreds that we have to sample. It's very difficult to use ANOVA. The next requirement is that all populations have the same standard deviation, or at least not too different if the sample sizes are nearly equal. I will not get into the details on how to check either of these two requirements, but I want you to be aware that don't just use ANOVA for really important research unless you've taken another statistics class and you understand how to check that these two assumptions are true. The next is what we've always been doing, is that the data collection uses simple random sampling, or at least you are approximating simple random sampling. In our first chapter, we talked about what it takes to be approximately simple random. You could do a stratified sampling technique or a cluster sampling technique, but don't use convenience sampling. The next is the samples are independent of each other. So we saw with two quantitative variables, we had independent samples, and then we had the paired dependent samples. So ANOVA does not work for dependent samples. That would be asking one person 10 questions and the next person the same 10 questions, etc., etc. Those would be dependent samples. This is for independent sampling. And then finally, the categorization of the sample is done in the same way for every other sample. So if we're using stratified sampling for one of them, we better use it for the others too. So make sure that we categorize, we just use the same processes for each of the samples that we take. So let's do an example. So the question is, are the mean driving speeds the same for Highway 50, Highway 89, and Pioneer Trail? So you could think that the police department might have clocked a bunch of the cars, and in the Highway 50 we had 58, 52, 51, etc., and then a bunch of speeds for 89 and a bunch of speeds for Pioneer Trail. And they want to find out if all the roads have the same average speed. So let's write down the null hypothesis. Notice we have three quantitative variables. The survey question is, how fast did that car go? And the answer is quantitative, 58 miles per hour. So H naught is that mu1, the mean speed on Highway 50, equals mu2, the mean speed on Highway 89, equals mu3, the mean speed on Pioneer Trail. And H1 is that at least two of these mean speeds differ from each other. Fortunately, the calculator can handle this. In the calculator, we're going to go to stat, tests, and then ANOVA. Then we'll use ANOVA L1, L2, L3. So let's go to our calculator. So here's the calculator. I hit the stat button. I need to enter my data. So I hit enter on edit. I need to clear my L1, L2, and L3. So let's do that. I go up to L3, hit clear, and enter, and do the same for L1 and L2. And then I just type in my numbers. For L1, that will be the first highway. So we got 58. Enter. And then all the way to 56. Enter. And then I go to L2, 43. Enter. and the final number is 58. And then I go to L3, 51, enter, 55, enter, and then finally 50, enter. So now that I have all of my data entered in the columns, I hit Stat again. I go to Tests. And not only is ANOVA the last test for this class, it's actually the last test for the calculator. So I will use the up arrow button to get to that last test. And you'll see ANOVA, and I hit Enter. Then I type second 1 for L1, comma, second 2 for L2, comma, second 3 for L3, end the parentheses, and hit Enter. So there we have it. Our F statistic, that's the test statistic, is about 1.92 or so. And the p-value is about 0.17. So let's go back to the PowerPoint. Now that we have the p-value, 0.175, notice that level of significance wasn't given in this problem. In the real world, no one gives you a level of significance. You look at the p-value and you make a decision. We have 0.175. That's bigger than any level of significance that we would ever use. So when we have a high p-value, the conclusion is fail to reject H0, the same as any other tests that we've done. That means there is insufficient evidence, and then we just state H0. Okay, or H1 since it's insufficient. And we say there is insufficient evidence to conclude that the population mean speeds on the 3 roads are not the same. So let's take a look at another example. So a study was done to see if the mean GPAs for in-state, out-of-state, and foreign students are different. What can be concluded at the 0.01 level of significance? So let's start out by talking about H0. First, this will be ANOVA because we have 3 different quantitative survey questions, and we want to find out if the means are not all the same. So H0 will be that mu1, the mean GPA for in-state students, equals mu2, the mean GPA for out-of-state students, equals mu3, the mean GPA for foreign students. And then H1 is that at least 2 of these mean GPAs differ from each other. Instead of going to the calculator on this, I want to show you what it looks like if you use a computer. Nobody really uses a calculator when it comes to truly doing statistics. Everybody uses computers. So this is what a readout would look like if you were using a computer. Lots and lots of things are given. We're given the 3 different variables. They are sample sizes, means, standard errors. We're also given all kinds of other math, and I'm not going to get into the details of this math. GFSS, MS. F statistic, that's our test statistic, is 13.47. And then the most important number of this entire course is always the p-value. And here the computer says less than 0.0001. So that's a tiny p-value. And when we have a tiny p-value, we can state our conclusion and say that there is statistically significant evidence to conclude that at least 2 of the population mean GPAs differ. So I'm going to show you one more example. This is the last example for the entire course of elementary statistics. And the question is, are the mean lifespans for dogs the same for different living conditions? And we have some data for dogs that live in a fenced yard, for dogs that really only live indoors, except maybe to take a walk on a leash, and then for dogs that are indoor-outdoor, so maybe outdoor in the daytime and they're kept indoor at night as a typical dog, and then stray dogs. So here's our data, and I want to remind you about something. There are all kinds of assumptions that we have to make in order to use the ANOVA test here. I really don't know if they're normal. We have to have a normal distribution for each of these 4 types of dogs' lifespans. That probably isn't even true. The sample sizes are tiny here. For the indoor-outdoor, the sample size is only 5. So you would probably not really do ANOVA or any test on this. But if I gave you an example where we had large enough sample sizes, it would just take too much time to type it out. It would be too big on the screen. So this is just for this class. In the real world, you better get a lot of dogs in each category, over 30 dogs in every category. Next, we really don't know if the standard deviations are the same for these 4 kinds of dogs. I have no clue. So we're just going to have to make that assumption. It's probably not even true. Beware of ANOVA. It's probably not the right test to use. But if we did know the standard deviations were the same, that might mean we could use ANOVA. But we also have to have that these are independent. That probably is true. If one dog is indoor only and another dog is stray, they probably have nothing to do with each other, for example. And we had to have simple random sampling or a scientific sampling technique. That just means you better do your due diligence and sample correctly. If you have all those things, then we could state the null hypothesis is that mu1, the mean lifespan for dogs that live in a fenced yard, equals mu2, the mean lifespan for dogs that are indoor only, equals mu3, the mean lifespan for the indoor-outdoor dogs, equals mu4, the mean lifespan for the stray dogs. And H1 is that at least 2 of these mean lifespans differ from each other. So let's go to our calculator and put in all this data and find out our test statistic and the p-value. So here's the calculator. I go to Stat, Enter, and I have to clear out each of the variables. Here, I clear out L4, it's already cleared. I clear out L3. I clear out L2. And I clear out L1. And then I type in all my data. I start with 15. Enter. And the final value is 8 to enter in the calculator. And now I have all of the data entered in. So next I go back to Stat. I go to Tests. I use my up arrow to get to ANOVA. I hit Enter. Now I have second 1, comma, second 2, comma, second 3, comma, second 4, because I have 4 different variables, L1, L2, L3, L4. I end the parentheses and hit Enter. So the F statistic, the test statistic, is F is equal to about 2.1. The p-value is about 0.13. So let's go back to the PowerPoint. Okay, so our p-value was 0.13. That's larger than any level of significance we might use. So when the p-value is larger than the level of significance, the conclusion is to fail to reject the null hypothesis, so that there is insufficient evidence to conclude that the population mean lifespans for the 4 dog lifestyles differ. That doesn't mean that they're not all the same. Notice that our sample sizes are tiny. When you have sample sizes that are tiny, you usually can't conclude anything. And even this test is a little questionable because we had all those assumptions to make. But given all the assumptions are true, we still just fail to reject the null hypothesis. So this is the very last example of the entire course. So instead of just saying goodbye, I think it's a good idea to go back and rehash all of the different tests that we've had. We've had so many different hypothesis tests, it could be confusing on which one to use. So let me go and talk about what test to use and how to ask yourself the right questions to decide which test to use. The first question you should ask yourself is a survey question quantitative or qualitative? If the survey question is qualitative, then in this class, the only test we know how to use is the chi-squared test. And if you remember, there were 3 different chi-squared tests that we had. The first was a test for independence. So we want to say, are these 2 categories independent of each other? Or is there a relationship between the categories? Remember, H naught was that the 2 were independent, and H1 was that the 2 were dependent. If it's not that case, then the other kind of question we have is, are the distributions the same? But if we happen to know the population distribution of one of them, and we don't know the other, we've only taken a sample, or if we're just checking to see if the distribution of a population is either uniform or normal, we use the goodness of fit test. The final chi-square test was asking, do these 2 populations have the same distribution? And we don't know about either population. We only have samples for each. And in that case, we use the chi-squared test for homogeneity. If we don't have qualitative data, if the survey question is quantitative, the next question you ask is how many samples were taken. If only 1 sample was taken, and if it was a yes-no question, and if the expected number of yeses and the expected number of nos are both greater than 5, then we use that 1 prop z test. If it's not a yes-no question, and if we happen to know the population standard deviation, and we have a sample size greater than 30, we use a z-test. If we don't know the population standard deviation, and it's quantitative, and the sample size is greater than 30, we use a t-test. So that's for 1 sample. What if there's 2 samples? So if there's 2 samples taken, well, if we want to predict y given x, that's regression analysis. And then if you remember, H naught was that the correlation was equal to 0, rho equals 0. And H1 was that rho was not equal to 0. On the other hand, if we had yes-no questions for both of these, and if we had NP and NQ, the number of yeses and the number of nos hypothesized for both data sets, we use a 2 prop z-test. That's the test for the difference between 2 population proportions. If we're looking for the difference between 2 dependent variables, So if we ask the same person two questions and we want to find out if there's a difference between their answers, or if we have, say, one day and there were two areas temperature on that day, and we want to find out if there's a difference in temperatures, and they're both quantitative, and we have surveyed more than 30, then we can use just a regular old t-test. But remember, we're not using a t-test on either of the two survey questions. We're using it on the difference between them. So that's the L1 minus L2 gets stored into L3, and we do a t-test on L3. If we have two samples, and they're quantitative, and both of the sample sizes are greater than 30, and now we have independent samples, and we know the standard deviations, then we use the two-sample z-test. So we use the test for the difference between two population means when we know the population standard deviation. If we don't know the population standard deviation, but we have two quantitative questions, and we know that both of the sample sizes are greater than 30, and the samples are independent, then we use the two-samp t-test, or the hypothesis test, for the difference between two independent samples. And then finally, we have today's big hypothesis, and that is if we have more than two samples, and they are quantitative questions, and we have all of those many assumptions met, we have to make sure normality, we have to make sure that the population standard deviations are the same for all of the different populations. We have to make sure that we've done a scientific study, that these variables are independent, and that we've categorized in all the same ways. If we have all of those assumptions, and if you take another statistics class and really understand how to do it, which you don't today, but maybe in the future someday you will, then you can run an ANOVA test. So that's all I have to say for this entire course. I hope you got something out of taking elementary statistics and an appreciation for how important statistics is in order to conduct research, to really have valid results. If we don't have statistics, you really have trouble doing any research. So if you have any questions about anything that happened in this lecture or this entire class, please let me know. I'll be happy to answer your questions. Ask your instructor, get help from your friends, from a tutor, whatever it takes. And I just hope that after today and after the final exam, which I'm sure you will all do really great in, that you'll use some statistics, that you'll remember some of the things that we did, or at least know how to go back to these videos, or go back to your book, or go back to me or your instructor. And when you need to conduct research, that you'll be able to do it in a professional way by making use of statistics properly. And you will be able to read other professionals' research and say, yes, they did their job right, or what are they talking about? This is nonsense. They don't get statistics. So hopefully you have learned how to critically analyze research, not just other people's research, but your own research, to make sure that statistics is used properly so that the research is valid. So have a wonderful life and use statistics well.